Welcome back to Multigrid Methods. So last class we started talking about analysis on vector space in this new chapter called convex optimization. So we're building up a very abstract theory for um, for optimizing functions. So actually this could be thought of as a basic short course on optimization theory. There'll be a course in the fall called 577 where this will be repeated, but maybe in the context of machine learning and things like that. And this we're going to be a little more abstract than in 577. We're going to use this Banach space setting. You can also do the same analysis in RN, but then you don't have as many tools and some of the theory doesn't come quite as easy. But we're going to have to pay the price of having to do things from a fairly high level. Most of you have seen Banach spaces and Hilbert spaces in a course on functional analysis or linear analysis. I think at this university it's called applied linear analysis. But in any case, we're reviewing all the key major concepts and we're going to go slowly. And if you have any questions about it, let me know. So what does it mean to do analysis on vector spaces? It means we want to try to understand concepts like continuity, concepts like convexity, minimization, differentiation for functions that are mappings from Banach spaces into other Banach spaces. And actually, more specifically and mostly, we're going to be interested in mappings from Banach spaces into the real numbers, the line, the real line. And so, yeah, I'll stop jabbering on about it, and we'll pick up where we left off last time. I'm going to back up one slide. So what we were talking about last time was weak convergence, and then we went into an example. So let's review our definition of what is weak convergence. Let X be a Banach space and X prime be its dual. This means X prime is the set of all bounded linear functions from X into R. So it's also written like this. Set of all bounded linear functions taking X into R, the real line. That's called the dual space. We say that the sequence Vn in X converges weakly to a point V in X if and only if the dual pairing, remember this was our symbol for what's called dual pairing. If you don't like that symbology, that notation, then you can just write it for it in its alternative form, which is a little less confusing. This simply means f evaluated at Vn minus V. Okay, so this object here, the dual pairing, is really just this object. So that limit f of Vn minus V has to go to 0, or it has to equal 0 for all f in the dual space. So this f is a bounded linear function or functional, and so this has to hold for every bounded linear functional. Last time I showed you very quickly how, based on the fact that this is bounded, that strong convergence implies weak convergence, and it doesn't hurt to redo that. So if I know that Vn converges to V strongly, then we're going to be able to conclude that it's also converging weakly. In other words, strong convergence always implies weak convergence. The proof is very simple. If I apply f to Vn minus V, and then if I use the boundedness or the continuity of this, there's some m for each fixed f, so I can put a subscript f. It only depends on what f is. It doesn't depend on what the points are, times the norm Vn minus V. And this is the norm in the space X. Well, this guy goes to 0 because if we're assuming that we have strong convergence, that means convergence in the norm. That means the norm of this difference is decreasing to 0 as n gets larger. But since mf is a constant independent of n, this means that this has to also converge to 0. So that means we have the basis for weak convergence. The fact that we can conclude weak convergence is the fact that this holds for any f that we want to put in there. This constant depends on f, but it's still a finite number and it's independent of n. That's the important part. So strong convergence implies weak convergence. So we were right in the middle of proving that the converse is not necessarily true. So we might have something which converges weakly, but something which definitely does not converge in the norm. And this example is one exactly like that. We're going to show in this example that this sequence defined by that, so this is a set of sine functions which are becoming even more wiggly, right? So let's see, what's n pi, so minus pi to pi. So roughly speaking, this guy, oh right, nx, it's going to look something like that, right? And then like that. I'm just plotting it on 0 to pi instead of the other way around. And it looks something like that. So the sequence is just sine functions. They're wiggling ever more rapidly. Well, the sequence of sine functions isn't converging to anything, and it's not hard to see that in a number of ways. The easiest way, perhaps, is to show that if I take Vm minus Vn, so I want to show that the sequence is not Cauchy. Why would I want to show it's not Cauchy? Well, if it's not Cauchy, it can't be convergent because L2 is a Hilbert space. If I have a Cauchy sequence where I know that a sequence is Cauchy if and only if it's convergent. Well, so let's show that it's definitely not Cauchy. And the easiest way to do that is for any m and n which are not equal to each other, then the difference of this in norm squared, the L2 norm squared, is equal exactly to 2 pi. So there's absolutely no way that this sequence can converge, right? This number is finite no matter what is the value of m and n. There are other ways I can show that it's not convergent. Now, on the other hand, we're going to show that this sequence converges weakly to 0. Doesn't converge strongly to anything, but it does converge weakly to 0. And this is really a restatement of the Riemann-Lebesgue lemma. And so let's prove this. So to obtain this, we're going to invoke the Riesz representation theorem, which says that any bounded linear functional can be written as an inner product. Okay, so if I grab any generic bounded linear functional, it's always going to have a representative, and the representative we're going to denote by f. So the bounded linear functional in its full generality can be written like this, no matter what it is. It's just going to be some integral of some function f against v. So we're mapping v into its integral against f, and that's going to define a linear functional. And in fact, that defines every kind of possible linear functional that there is. F here is called the representer, or if we want to think about mapping the linear functional to f, this is the value of the Riesz map. So now we need a fact from measure theory that you may or may not recall. And it says this, step functions, the sequences of step functions are dense in L2. So if I fix f in L2 and I pick an epsilon, then I can always find a step function which is within epsilon in the norm away from f. So I can always build a step function, and this is the step function that I want to build, that if I take the difference between f and epsilon in norm is less than any small amount that I want. And it turns out what's easiest for me to do for this proof is to make it epsilon over 2 square root of pi, all right? So this is an arbitrarily sized number, and I can get f epsilon arbitrarily close to f. What does this look like? So remember, L2 functions can be pretty scary. And so I'm not going to look at a general L2 function, but let's look at something which is at least continuous. So I can approximate that by a step function. And the step functions, of course, look like this, right? This is not quite as simple as something called a simple function that you may be familiar with from measure theory. Step functions are, or I should say, it's a little more structured than that. These are the same step functions that appear when you're defining Riemann integration, okay? So it's not quite, I should have said, not quite as basic as what's called a simple function. All right, so this is the general form of a step function, at least the ones we're going to be interested in. And this is just the, these little pillars here that you would construct. Right, so this is guaranteed to us from measure theory. So let's put that in our pocket for now. And by the way, how do you construct a step function? You need a partition, right? And then it's going to take values over intervals of the partition, etc. So it looks exactly as I've drawn here. All right, so now we're going to consider, or we're going to try to show that this integral always goes to 0. So let's label that in. We just want to show that this integral goes to 0, but let's estimate this in a specific way. All right, so how do I want to estimate this? The first thing I'm going to do is I'm going to look at this f here, and I'm going to subtract and add f epsilon, or add and subtract, however you want to do it. And then I'm going to apply the Cauchy-Schwarz inequality and the triangle inequality. So I'm going to do this in 2 steps. The 2 steps are, I'm going to write that integral as minus pi to pi, f minus f epsilon plus f epsilon, right, Vn dx. I guess apply the triangle inequality first if you want, and then the next step is to apply Cauchy-Schwarz. Okay, triangle inequality first, Cauchy-Schwarz second. So if I apply Cauchy-Schwarz to the first part that comes out, that is this times that, then this is what I get. Okay, L2 norm of the difference, f minus f epsilon times Vn, both in norm, and then plus this integral here, okay, which doesn't look like a nice integral. Now, about the first thing, well, this can be made arbitrarily small, right? Based on the argument that we had over here. Okay, it can be made arbitrarily small. And what about the next thing here? Well, now for this guy, all we need to do is figure out what is the L2 norm of that. And this is precisely set up to be square root of pi. So that whenever I multiply those 2 numbers together, I get the cancellation of the square root of pi, and all that remains is epsilon over 2. The next step is, let's focus on this integral. Okay, so that calculation is completely independent of n. It doesn't matter what it is. Always going to get square root of pi. Now let's move on to this calculation. What is going on with this guy? Well, let's break this guy up into its definition, and then again we can apply the triangle inequality. So we write that according to its definition. We're going to apply the triangle inequality a number of times, right? Well, exactly m times. The partition size is m. All right, so then we're going to calculate the, let's see here, what's the next? So, okay, so now we have this guy, right? This guy is going to come out. In fact, let's take the maximum of that, right? So we can replace this by its maximum and then find also the maximum of this guy. There are other ways you can do it. You don't have to take the maximum here. Now, where is this m coming from? Well, the m comes from, we're taking the maximum, so we're going to have to replace everything else by that maximum. And we're replacing n terms in the maximum, so we get an m out front, okay? So this is the same as if I were to say, okay, I want to replace sum I equals 1 to m, right? So this is going to be m times the max over I of AI, right? It's just that I have um, a couple of terms in there to take the maximum of. Okay, so that takes care of that. These are just numbers. But what about this guy? So let's see if we can control the size of that. See if we can control the size of that. Well, this is just going to be um, for at least a finite given interval. These are just integrals of sine functions over small intervals, right? Let's focus in on this guy and fix our partition for just a second and think about taking n going to infinity. Let's think about what we get. So let's do this as a side computation. All right. So for any points CL to CR in this interval minus pi to pi, let's calculate this interval here. Well, this just involves calculating this integral exactly using the fundamental theorem of calculus. And the largest that this integral could be is equal to 2 over n for each one of these intervals. Doesn't matter what the value of CL or CR is. So we can replace each one of those integrals by 2 over n. 2 over n, okay? And so this just becomes, the whole max just becomes 2 over n. So let's go on a little bit further. So now, whenever we fix f and epsilon, then that fixes the size of the partition that we want to use. The partition's not going to get any bigger. Basically, once we fix f and epsilon, that number stays fixed. Okay? And this set of numbers stays fixed. We don't have to worry about them growing unbounded or anything like that. So the next step is to say, well, okay, if those things don't grow unbounded, m or the maximum, well, then let's choose n to be bigger than this number here. Okay, whatever this number is. This is not necessarily an integer, it's just some number. We can certainly choose an integer n which is larger than this whole number. Okay, now this has been perfectly contrived so that once I put that information back in this step right here, then this whole term works out to be exactly epsilon over 2. So I have an epsilon over 2, an epsilon over 2, based on my choice of n. Notice that these other numbers here don't depend at all on m. This is simply, it is what it is, also whatever it is. And this guy is the only place where there is some n dependence. This is 2 over n. So if I pick n to be this large, actually, I apologize. I didn't realize that this was actually, this is the largest integer, right? So I thought that was a bracket at first. So this actually is an integer. Okay, so we're taking the largest possible integer in this number. Let's see, actually that is, the ceiling function actually is the rounding up of that, right? So in any case, it's an integer. It's a positive integer. And so this guy here is an integer, okay? It's greater than that integer. All right, so this whole term, as I said, still works out to just be epsilon over 2. So what we've shown then is that in is less than epsilon for any epsilon that we want to choose. And, right? And so the only thing that is really that matters here is that we're fixing f. Once f is fixed, then we can think about choosing epsilon. Okay, so we fix f first, then we pick epsilon and leave that fixed. Once that's fixed, then we can pick m, and then we can pick this partition, etc. Well, so what that's saying is that for every fixed f, we can say that in has to be less than epsilon as long as n is bigger than some number. All right. Well, this says that in must be converging to 0. That's the only possible thing. Of course, we also know that in is larger than 0, right? Greater than or equal to 0. And it's kind of getting smushed down to 0. That's the only place that it's going to be allowed to go. In has to converge to 0 as n gets larger and larger. All right, so we've proven exactly what we wanted to show. In converges to 0. So that says that that sequence, which we started out with, which is not convergent, it's not Cauchy, it's not convergent, is, however, weakly convergent to 0. And the reason it's weakly convergent is because for every bounded linear functional, which can be uniquely represented like this, it turns out, through the Riesz representation theorem, okay, for every linear functional, we can show that that linear functional, Vn, converges to 0. Now you might object and say, wasn't it supposed to be Vn minus V, the limit, or yeah, the sequence minus its limit point? Well, this limit point in this case is just the 0 function. Okay, it's just the 0 function, so that's gone. So that's all we need to show is this guy here, and we've done that. And so there's an example of a sequence which doesn't converge strongly but does converge weakly. So weird things can happen in infinite dimensional spaces. And this is exactly what we have here, an infinite dimensional Hilbert space. Now we can say a lot more about analysis in Banach spaces, but we're only going to say what we need for our convex optimization problems that we're going to encounter. So we're going to turn our attention now to nonlinear mappings that are going to be useful to us. All right, so for the most part, we're going to be interested in nonlinear functionals. And what do we mean by that? I mean, V could be a Hilbert space or a Banach space. We're going to stick to the Hilbert space case that takes points in the Hilbert space and maps them into R. And we're not going to assume anything about this function being linear or bounded or anything like that. And so this gives rise to something called a nonlinear functional. So that's what we're going to be mostly interested in the rest of this section. Nonlinear functionals and their differentiability and convexity and things like that. Nonlinear functionals. It's called a functional because it's going to map an object into R. And this object could be itself a function. So for example, V could be the Hilbert space L2. So I could map functions into R. How would that work? Well, the integral is one good example, but the problem is there, it's linear. So what's an example of a nonlinear functional? Well, I could take something, let's say, let's just use the case of a Banach space. So I'll give you an example of a nonlinear functional. Let's look at the example where for the Banach space, let's use this guy, C0. So that's not a Hilbert space, but it is a Banach space. It's a Banach space if we pair this with the sup norm. And so they're continuous functional. So here's how I'm going to define, continuous functions. Here's how I'm going to define this nonlinear functional E. So we're going to say that this guy is the integral of U absolute value quantity cubed dx. Right? So this is not linear because the integrand is no longer linear. The fact that we're cubing this takes us from a linear operation into a nonlinear operation. So it's definitely not linear anymore. However, will this object make sense? Well, it is the cube of the absolute value of this function still integrable over 0, 1? The answer is yes, because the whole thing, this guy is a continuous function. If I take the absolute value of a continuous function, then that's continuous. And if I cube that result, then I get a continuous function again. And every continuous function on the closed compact interval 0 to 1 is integrable, and it gives us a number. So this guy is going to give us a number. And whatever it is, we don't know necessarily off the top of our head. This is going to be a real number. So there's an example of a nonlinear functional. Nonlinear functional. So it takes a full function and it's going to map it to some real number. Now, for these things, we're going to be interested in things like continuity and differentiability. We're going to be interested in this weird concept that you may have never seen before, and this is because it has something very useful to say in the context of optimization. And this is the notion of what's called lower semi-continuity. So let's let V be a Hilbert space. Suppose that this is a nonlinear functional. Okay, well, it's just a functional. It could be linear, but it's most likely going to be nonlinear. We say that E is a lower semi-continuous, LSC, if and only if at V, if and only if whenever Vn converges strongly to V in the Hilbert space, right? So there's a notion of strong convergence, and that's the norm convergence in the Hilbert space. Hilbert spaces have an inner product and a norm which is built from that inner product. So it definitely has a norm on it, and we can definitely talk about the strong convergence. By the way, strong convergence is always symbolized by the usual arrow. So it's lower semi-continuous if and only if for every sequence that converges strongly to V, we have the following thing holding. So E of V is less than or equal to the lim inf of EVN. So what is the lim inf? So remember, for sequences, a bounded sequence doesn't necessarily have a limit, right? So you should think about this as a sequence. Now, this is one sequence. What happens whenever we apply E to Vn? That is also going to give us a sequence. It's a sequence of real numbers. So EVN can be mapped like this. So I can look at this function of n, or the functional values of EVN as functions of n, and map them according to the values of n. So that might start out looking like that, right? But then all of a sudden it could just wiggle and wiggle and wiggle. It doesn't necessarily have a limit. But let's assume for the moment it's bounded, right? So what can we say about that? It doesn't have a limit necessarily, but it does have a lim inf and a lim sup. So the lim inf is going to be the thing to which this kind of lower envelope that you converge to. And the lim sup is going to be the upper envelope that you converge to, the upper bound. Okay, so I'm not going to remind you of the precise definition of that. That's from analysis, which you hopefully remember. But this is the lower of the limits, right? The lim sup would be the upper, the lim inf is the lower. So all we need for this to hold true is that for every V, or at this point V, for every sequence that converges to V, then we have this holding. So again, this is a sequence. This is its pre-image, but this is a new sequence which might, even though this guy converges, this guy doesn't necessarily converge to anything. But we need its lower envelope to converge to something which is bigger than EV. And if that happens, then we say that E is lower semi-continuous at V. We say similarly that E is weakly lower semi-continuous, or WLSC at V, if and only if basically the same stuff happens, except that we're going to say whenever Vn converges weakly to V. So this is our symbol for weak convergence. Okay, so go back to the definition. So our symbol for weak convergence is here. I forgot to emphasize that. It's an arrow, but with only has the top prong on it, sometimes called a harpoon. Only the top prong. So if and only if, whenever Vn converges to V weakly, then we have the same punchline. Now again, this guy is a sequence. This guy is also a sequence. That's the image of that sequence. This may or may not have any kind of limit associated to it. All right, but its lim_inf and lim_sup will be they'll be finite as long as this is a bounded sequence. And let's go ahead and assume that it is a bounded sequence. If it's a bounded sequence, then the lim_inf and the lim_sup will both exist. The limit doesn't necessarily exist, but the lim_inf and lim_sup both exist. And what we're saying is this EV has to be less than or equal to the lim_inf. If that's true, then we say that it's weakly lower semi-continuous. All right, if K is a subset of V and E is weakly lower semi-continuous for every point V and K, then we say it's weakly or just lower semi-continuous on the whole set K. And I guess this could be, I have here a strict subset, but it could be less than or, K could be equal to V. But that, in that case, we just say that it's weakly lower semi-continuous for every point. Okay, so that's lower semi-continuity and weakly lower semi-continuity. I'll show you a picture of what we mean by semi-continuity momentarily. What does it look like for a function? What does a function that's lower semi-continuous look like? So I'll show you that. So before we do that, let's get on to a couple more definitions. Suppose that, again, V is a Hilbert space and E is a functional. The epigraph of E is the set of points from VR, V cross R, V alpha in V cross R, the set of all points, such that E of V is less than or equal to alpha. See, I have a picture on the next page. Okay, so here's a function of here's a graph of a function which has a couple of points of discontinuity, okay? What is the epigraph? The epigraph, okay, so along this axis is just regular good old R. Now up here you should think about this, actually I got that wrong. So this axis is regular old R, and this axis we're going to imagine that is the Hilbert space. So the epigraph is everything above, essentially everything which lies above the graph. Okay, so it's everything up here, and it has to be greater than points V alpha such that alpha is greater than or equal to E of V. So let's look at this point right here. So there's my V. What points are greater than or equal to that? Well, everything on that line above it is. Okay, so I can include all of those points. Everything going up that way. Same here, everything above this point, right? And everything above that line. All right, so that purple shaded set is the epigraph. We can do the same thing over here with this function, right? And I'll color this in orange. So all the points above the points on the curve, and we have to do something a little bit different at, say, this point here. So I need to find all the points alpha that are above this point E of V. What about this point here? Those points aren't in there. These points in between, because the value of E of V is actually here. So it has to be all the points above that point. So only those points are gathered in there. But there's something about these points here that are left out. Okay? We can get arbitrarily up close to those, but those points are left out. And then once again, we have that. So It turns out that this function over here is not lower semi-continuous. And this function over here is lower semi-continuous. All right, there's one glaring difference between these two shaded region sets. This shaded region set up here, this epigraph, is a closed set. Okay, and that's because all of the points along this line and this line here were included in the set. So all of its points of closure are in the set. So this set over here, this epigraph is closed. This guy is not closed. It's not open, it's not closed, it's neither. And the reason is because of the points which were left out of here. Okay, it's like the difference between, okay, if I have a circle, right, or disk, and I say everything inside the disk and what is on the boundary is part of the set, then that's closed. But what if I give you an open set or an open disk? So everything up to the boundary, but not on the boundary, right? And so these points here in that definition would be left out of the set. Well, those are limit points. So this set here is not open, whereas this set, because it includes those points in the boundary, are open. And so it's the same reason, or the same line of reasoning. Because I'm not including these points here on the boundary, this set is open. There's some defect right there. It turns out this epigraph is closed. This epigraph is not closed. So we'll get there in a second. But in any case, that is the epigraph of those particular functions. Here's how it's defined generally. It has to be the set of all points v and alpha, so that's in v cross r, such that e of v is less than or equal to alpha. All right, that's the epigraph. I also need another definition, which we're going to use later. Let v be a Hilbert space and e be a nonlinear functional, and alpha be some number in R. Then the sublevel set at height alpha of E, which is denoted like this, level sub alpha of E, is equal to the set of all points in the Hilbert space, such that E of V is less than or equal to alpha. So this one is much easier to visualize. If I have a function like this, okay, so there's my E, and if I have an alpha, which is here, right? So then if I'm looking for all the points V from the Hilbert space, which satisfy that inequality, then what points do I need to be looking at? Well, basically I'm going to draw some sort of curve like that. And then I realize, well, everything in this interval, let's make it a color. Everything in that purple interval, purple shaded interval, has the property that E of V is less than or equal to alpha. So for this case, this would be called, or this would be the unique sublevel set of that function. Okay, well, or the sublevel set at height alpha. Now, what if I increase the value of alpha? If I increase the value of alpha, then that set gets bigger. What happens if I decrease the set or the value of alpha? Well, I could decrease the set of alpha, let's say to here, right? Let's use a let's use a different color there. I could decrease the alpha further, something like that. So that would be that set. I could decrease the alpha further still until basically the sublevel set was empty. There's no points. For example, for this value of alpha, there are no points in the Hilbert space such that E of V is smaller than alpha. There aren't any. Okay, so that in that case, that sublevel set is just the empty set. All right, so those are two important sets that we need to consider when we talk about convex optimization. Epigraph, which is everything above the graph, essentially, and the sublevel set. Okay, so there were our pictures that we drew earlier. And now we have this, let's see. Why did I redefine that? Let's see. I think I might have gotten screwed up in my notes here. Let's just see. Yeah, I didn't need to redefine this. Um, I I probably had this as a frame that I was gonna kill and just forgot to do it. So you can just disregard that. This is a definition we already gave. All right, this is the thing that I wanted to get to. Okay. Says something important about weakly lower semi-continuous functions in the epigraph. Let V be a Hilbert space and E be a nonlinear functional. The functional E is weakly lower semi-continuous or just regularly lower semi-continuous. You can omit this word weakly. If you put it there, then you put it in every location that's in the parentheses. And if you omit it, then you omit it in every location. So let's read it without the weakly present first. The functional E is lower semi-continuous if and only if its epigraph is closed, if and only if for every alpha and R, the level set or the sublevel set, level alpha E is closed as well. Okay, so there's two equivalent ways that we can express the fact that, well, I guess three now. There are three equivalent ways that we can say that a function is lower semi-continuous. We can either use the definition, or we can show that its epigraph is closed, or we could show that the sub-level set E is weakly closed, or sorry, the sub-level set of E is also closed. So those are three different equivalent statements. The definition, the closure of the epigraph, or the closure of the sub-level set for every alpha. Now you can go back and put the weakly in there. So it's weakly lower semi-continuous if and only if the epigraph is weakly closed. And if and only if for every alpha in R, the sub-level set level alpha E is weakly closed for every alpha. Okay, so that's left as an exercise. It's just basically juggling definitions. So we can go back to our picture then. And in light of that, that result, this graph here, because it's clearly its epigraph is not closed, then this function here is not lower semi-continuous. What about this guy? This epigraph is closed, and therefore it's a lower semi-continuous function. Okay, so that's exactly what the caption says. All right. So we just need to edit our slides, and let's put that in red. Redundant slide, not needed. Okay, so three ways of expressing the fact that a function is, or determining whether a function is lower semi-continuous and weakly lower semi-continuous. All right, now we're going to turn our attention to the question of differentiating functions that are not necessarily sort of standard. Again, we're looking at functions that are from a Banach space into R, but let's back up and be even more general for now, okay? So let's just consider functions which are mappings from one Banach space into another. So this is what's called Banach space differentiation, and it's just a generalization of what we mean by the usual derivative. So we say, sorry, let's start off by our assumptions. Let X and Y be Banach spaces and F be some mapping between the Banach spaces X and Y. Domain is X, the range is Y. We say that F is Fréchet differentiable at V in X. Okay, so we're going to fix the point. So think about it like this. Here's our big space, X. And remember, F is going to take X into Y. And we're going to start off with a point in just some fixed point in X. Okay, that's going to get mapped over here to f of v, right? And the question if is this mapping differentiable at that point v? And it is if the following definition is satisfied. We say that f is Fréchet differentiable at v if and only if there is a mapping, a linear mapping actually, T. Well, it's not even just that. It's got to be a bounded linear mapping between X and Y, or the other way of saying that is a continuous linear mapping. Bounded linear mappings, continuous linear mappings are actually equivalent as long as the mapping is linear, such that the limit as the norm of H goes to 0. We could just write this as H goes to the 0 point in the space, but this is equivalent. The norm of H goes to 0 of this quotient. This is called the difference quotient, right? So in these Banach space mappings, H and everything in the image gets normed with the X norm, and everything in the I might have said that wrong. Everything in the pre-image gets mapped or gets normed with X. Everything in the image gets normed with Y. Okay, so what we want to show is the thing on the top divided by the thing on the bottom is going to 0. Now, what's on the top? The top has the usual sort of pieces that you would find in a difference quotient, right? F of V plus H minus F of V. Okay, so that's the usual thing. What's different is we're going to put the derivative map as a part of the numerator in the difference quotient. So that's it right there. This guy here is our target derivative. So if all of this stuff on the top, okay, when measured in the y norm and then divided by the norm of y has limit 0 as h goes to 0, then we say that this is Fréchet differentiable. Now, there's no way to motivate this through a picture. This is just a generalization of the idea of the derivative. However, if you go back and look and think about, well, what's the definition, the usual definition of something being differentiable? I took limit as h goes to 0 of f of, let's put things in the terms we usually understand, f of x plus h minus f of x over h. That has to be equal to some number, and that number we usually called f prime at x, right? Well, now we're not going to call that f prime, we're going to call it t. We can call the derivative whatever we want, okay? All right, so now we could multiply t by h, right? And we can bring it to the other side because, well, this is entirely equivalent to the following statement. Let's just say that. This is entirely equivalent to saying that f of x plus h minus f of x. Let's put this t in this quotient. Well, if we do that, we're going to do th over h, and that's got to be equal to 0. Okay, so this, I claim, these are two entirely equivalent statements. And the next thing I can do is put absolute values around the top and the bottom, and that's an entirely equivalent statement to the previous. And so you can see that this matches essentially that definition above there. It's so you can see, I hope, why this is a generalization of this usual stuff. Now, it's not normal, I think, to think about t as being a linear operator, simply a number. But actually, I can think about a number as being a linear operator. It's a linear mapping under the multiplication operation. And so this number that I have down here really is a linear operator from x, which in this case is just going to be the real number line, into y, which again is the real number line. All right, so I'm not expecting you to get a geometrical feeling for what is going on with this definition. It's simply a generalization. If this t can be found, so that's actually going to be the derivative in this case, t. If this linear mapping between x and y can be found, then we say that it's Fréchet differentiable at v. Now it turns out, just like the derivative case, because limits happen to be unique in the ordinary derivative case, this Fréchet derivative, if it exists, has to be unique. If it exists, if this t exists and we can find it, then it has to be unique. There can be no other ones. That's good. That tells us that this concept of differentiation matches our intuition from the one-dimensional case where derivatives were unique. What else can we say about this? Well, let's give it a more proper name. Instead of calling it t all the time, let's give it this symbol. Let's call it df of v. So for every fixed v, we're going to generate a new mapping. Okay, it's going to be a bounded linear function from x into y, or a bounded linear mapping, a bounded linear operator from x into y. Now we say if k is some subset, and I probably again should do, I should say k it can be all of x, and f is Fréchet differentiable at every v of k, then we say f is Fréchet differentiable on all of k. Sometimes people put in there that k should be an open set. It doesn't really matter what the set looks like. All right, so what about if we have a derivative of a functional? A functional is an operator which takes v into r. So in other words, the second space is going to be sort of the quintessential Banach space or Hilbert space. It's just going to be r. All right, so in this case, if this mapping is differentiable, then the Fréchet derivative, if it exists, is going to be a bounded linear functional, right? Because if that derivative exists, then we're going to say if at some point this guy exists, then it has to be in this space, L, V, the first space we're going to make into a Hilbert space rather than just being a Banach space. Hilbert space means it is a Banach space, but it's got a little bit more structure. All right. And we're going to make the second space be the real number line R. So that's like saying X is V, a Hilbert space, and Y is R, the real line. Well, this space, we have a special name for it. That's just going to be V prime. That's going to be the dual space. So in this case, we have the derivative, if it exists, is an element of the dual space. And remember, we had the special notation for duality pairing whenever we were in the dual space. So we said, let's make life a little bit more confusing for ourselves in some cases and define this notation here. That's the dual pairing of a functional with its with the preimage. And that maps to something which is in R. And so that's just using this definition of the duality pairing, which we discussed last time. So remember, if I have f being a function from the dual space, then the notation that we introduced called the dual pairing was f with, let's say, u, and that just meant f acting on u. Now, there's two things I want you to be aware of. Oftentimes, whenever f is a linear operator, then the parentheses are dropped. And people just write something like this. This is for the same reason that when we write with matrix vector multiplication, we write a times x, right? You don't write a parentheses x. You just do a times x. All right. Well, let's just get rid of that whole thing. That's why in this case, we didn't put an extra set of parentheses. That would be, you know, you could put an extra set of parentheses, but it kind of starts getting messy. So we're just going to drop that second set. The understanding is so this is the functional, and it's acting on that to produce a real number. Okay, so just keep that in mind. Okay, now once we establish a mapping, or once we have a functional and we determine that it is going to be Fréchet differentiable at a point, we can then ask, well, is that derivative a continuous function? If the derivative is a continuous function, then we say it's continuously differentiable. The same as if we're dealing with the usual functions of real variables. So let x and y be Banach spaces, and suppose that f is a mapping from x to y. We're going to suppose that f is Fréchet differentiable at every point of the set k in x, or what? Every point of the set k, which is a subset of x. The derivative defines a mapping, right? The derivative mapping takes v and it maps it to, so I can think about starting with a point, and then what is the derivative? The derivative is going to be a linear mapping. So you map points to a linear mapping. That's kind of weird. You can think about it like this. I've got my space x, and f takes x to y, right? That's what x does. It takes ordinary points, v, and it's going to map them to f of v. But what does a derivative mapping do? The derivative mapping is a little bit different. You have to be careful. So if it's differentiable at a bunch of points in a set, or all the points in a set k, then we have this derivative mapping called df. Now, every point over here, or these points over here, are going to be bounded linear functionals, or bounded linear operators, I should say. So once I reach this point over here, what is that object? df of v. It's not a simple point in a simple Banach space anymore. It's a function, okay? It's a linear operator now. So this set might get mapped to these, I don't know, this squiggly set here. This is the image of k under this differentiation mapping. All right? So it's getting mapped over here to this space. Now this, we said, if y is a Banach space, we concluded with a theorem last time that said this space of operators is also a Banach space. If y is a Banach space, then the space of operators is also a Banach space. So that might be something useful for you. But now we're going to be interested in understanding this mapping, this differentiation mapping, which takes x into Lxy, just like I said here. All right, so if this mapping is a continuous mapping, so what does it mean to be continuous from this complicated space to this complicated space? Well, it means that the inverse image of open sets is open if you've taken topology before, or we have a continuity definition of, or we have a sequential definition of continuity that you may have seen before. Either one of those will work just fine. So, for example, we could use the sequential definition. So if we have Vn converging strongly to V, we're going to use the strong topology continuity, then df Vn has got to converge strongly to, so this is in X space, right? And this is going to be strongly in the Y space to dfv. But remember, I made a mistake here, right? So this is not Y. This is going to be in the topology of the target. So that's going to be Lxy. Okay? Because each time I change this point, I'm going to get a new bounded linear mapping, and that's going to converge to this bounded linear mapping. So that's what we mean by continuity. in this case. But if it's continuous on this whole set K, then we say that F is continuously Fréchet differentiable on K. F is continuously Fréchet differentiable on K. All right, now the thing that makes this all hard, makes it complicated, is the fact that we're dealing with mappings from Banach spaces into Banach spaces. No longer just going to be mappings from real line into real line. It's a bit harder. So we talked about differentiable functions. We talked about lower semi-continuous functions. The next type of function, well, actually, I'm getting ahead of myself. I was going to say we want to talk about convex functions. We're going to wait on that just a second. I do, however, need a concept of what's called a convex set. And that will come back when we talk about convex functions in a minute. Well, maybe not today, but next time. All right, so what do we mean by a convex set of subset of a Hilbert space or a Banach space? So I think once again I want to use subset eq. What do we mean by a convex set? Well, I like to think about this in terms of sets that I can draw. So a set like that, which looks a bit like a deformed bean, turns out not to be convex. But a set like that is convex. And why? Well, the definition explains why. I want to take any points V and W in that space. I want to draw a connecting line between the two. All right. And I want to say that if this is going to be convex, all the points along that connecting line should be elements of the set. Well, you can see that that doesn't happen in this case. All right. So I can think about this as being, this connecting line as being an interpolation or interpolating set, or what's called a homotopic set. So I can use that, I can do that through a parameter t, such that if t is equal to 1, then I'm at V, and if t is equal to 0, I'm at W. So going naturally from 0 to 1, I go along this line sort of at a linear speed. I want all those points to be in the set for this set to be convex. That doesn't happen in this case on the left, right? So that's not convex. This set over here on the right is, however, convex, and that's because for any 2 points that I put in the set and make a connecting line, all the points on that connecting line are going to reside within the set. Okay, so that's exactly what this definition says. We say that K is convex if and only if whenever V and W are nope, that's not right. That's a typo. That should be K, right? Not for all V and W in X, but in K. All right, so whenever V and W are in K and T is some number between 0 and 1, then that interpolation between the 2 points always has to be in K. And if that happens, we say that the set is convex. So this guy clearly is not, okay, definitely not, and this guy is convex. If F is continuously differentiable on a convex set, then we have a nice analog of what's called Taylor's theorem. And the way you can prove this is, well, let's see, I guess it's not so easy to prove it in this sort of general setting, but it is for the functional setting. But we're going to just state it in its completely general way. All right, so let X and Y be Banach spaces, and suppose that F is continuously Fréchet differentiable on the convex set K contained in X. Then for every V and W in K, we have the following version of Taylor's theorem. F of W is equal to F of, or minus F of V is equal to an integral difference. So this is kind of like the remainder, right? And this is the usual thing. So let's just suppose that we have the usual setting R to R. f from r to r. Then this is going to be written like this. F of w equals f of v, right? So v is the expansion point plus the derivative of f at v times w minus v plus 1/2 f double prime. Let's just differentiate as many times as we want here. Blah, blah, blah. Well, so when we're not in one dimension anymore, we have to generalize this. What if we were in R? What if we were mapping Rn to Rn? So this is one that we commonly use in numerical analysis. Well, this stuff still makes sense, except that we have to make some changes here, right? So this guy here has to be a dot product because this gradient or this derivative here of f is now a gradient, right? And by the way, the gradient is a linear operator. So grad f, right? And now what about this guy here? This is going to be the Hessian matrix. And so I'm going to have to use some other expression here. And that expression is going to be plus 1/2. What is the expression? It's going to be v minus w. So these are vectors now, right? Transpose times the Hessian matrix of f, evaluated at some weird squiggle point, w minus v, right? So we have to modify this as f gets more complicated. And we can write a version of this, in this case, that involves an integration. I'm not going to write that out, but basically it looks exactly like this, right? So this is Taylor's theorem with integral remainder if I'm only going up, or I'm only assuming that f is continuously Fréchet differentiable. Now, why do I need this set K to be convex? Well, the reason I need it to be convex is I want this to be differentiable at every point K, okay? And that, of course, is what I'm assuming. In this integral, inside this function here, I need to consider all these points along this line. And all of these points along this line have to be back in K in order for this derivative to make sense. If I didn't consider a convex set, then this point might be outside of K, and this wouldn't be differentiable anymore. Maybe it doesn't. Maybe it's not differentiable at that point outside of the set K. And so that's why I need to consider a set to be convex. Maybe next time, we're running low on time right now, but I'll show you a generalization from this setting, one that we use commonly in numerical analysis, which uses the integral remainder. Okay, so in that case, this would be the gradient here. This would just be, well, we could do it right now, I guess. We've got a couple minutes. So what would this look like in the case where we had this f from Rn to R as we have down here? What would this look like? So let's do exactly that. F from Rn to R. What does it look like, this result that we have just up above? Well, it's going to be similar. It's going to be f of w, but w is going to be a vector minus f of v. V also is going to be a vector. And then this integral, you can check that this all makes sense, is going to be of the gradient of f evaluated at the points t w plus 1 minus t v, right? And this has to be dotted with w minus v, because that's how that gradient operator acts as a linear operator through the dot product. All right, so now this all makes sense, right? Because this guy here, when I dot it with this, is a real number. I can integrate this guy as a standard function, real valued function. What about this guy here? This guy here is a little bit different because the result of this function is going to be some numbers that end up back in the space y. Okay, this is something in y, this is something in y, so that difference is going to give you something in y, and this integral is going to result in something in y. And I haven't explained what we mean when we integrate a function, a Banach space function, valued function before, but this does have a meaning. And maybe I'll, at the very beginning of class next time, we'll talk a couple of minutes about that. So I'm going to end there. The next time we're going to pick up with talking about what does it mean to be twice Fréchet differentiable, and then what the heck does a second derivative look like? We already know a first derivative is quite complicated. How much more complicated are second derivatives? Well, it turns out second derivatives aren't that much more complicated, as we'll see next time. So with that, I'll take any questions you guys have.